The task for today is to find particular solutions. So let me remind you of where we've gotten to. We're talking about the second order equation with constant coefficients, which you can think of as modeling springs or simple electrical circuits. But what's different now is that the right-hand side is an input which is not zero. So we're considering the I'm going to use X as your book does, keeping to a neutral letter, but again in the applications and in many of the applications at any rate, it wants to be T, but I make it X. So the independent variable is X, and the problem is remember that to find a particular solution, and the reason why we want to do that is then the general solution will be of the form y equals that particular solution plus the complementary solution, the general solution to the reduced equation, which we can write this way. So all the work depends upon finding out what that yp is, and that's what we're going to talk about today. Now, or rather talk about for 2 weeks. But the point is, not all functions that you could write on the right-hand side are equally interesting. There's one kind which is far more interesting or more important in the applications than all the others, and that's the one out of which, in fact, as you'll see later on this week and next week, an arbitrary function can be built out of these simple functions. So the important function is on the right-hand side to be able to solve it when it's a simple exponential. But if you allow me to make it a complex exponential, here are the important right-hand sides where we want. We want to be able to do it when it's of the form e to the ax. In general, that will be, in most applications, a is not a growing exponential, but a decaying exponential. So typically a is negative, but it doesn't have to be. I'll put it in parentheses, though, often. That's not any assumption that I'm going to make today. It's just culture. Well, we want to be able to do it for sine omega x and cosine omega x. In other words, when the right-hand side is a pure oscillation. That's another important type of input, both for electrical circuits, think alternating current, or the spring systems, that's a pure vibration you're imposing a pure vibration on the spring mass dashpot system, and you want to see how it responds to that. Or you can put them together and make these decaying oscillations. So we could also have something like e to the ax times sine omega x or times cosine omega x. Now the point is, all of these together are really just special cases of one general thing, exponential, if you allow the exponent not to be a real number, but to be a complex number. So they're all special cases of e to the, I'll write it alpha x. Well, why don't we write it of a plus I omega x, right? If omega is 0, then I've got this case. If a is 0, I've got this case, separating into its real and imaginary parts. And if neither is 0, I have this case. But I don't want to keep writing a plus I omega all the time, so I'm going to write that simply as e to the alpha x, and you understand that alpha is a complex number now. Looks different, doesn't look like a real number. Okay, I make it, so it's a complex number.